In northwestern Montana, the ground is still locked under snow when the first machine starts. A harvester closes its head around a lodgepole pine. Feed rollers pull the stem through. Knives strip the limbs. Sensors count the length as it passes. In under a minute, a tree that stood for 80 years becomes 4 numbered logs lying in the snow. That is the part everyone films. Here is the part nobody films. That tree spent 8 decades accumulating value, and it will spend the next 10 seconds having most of that value decided by a computer in a scan tunnel 1,200 miles away. Because a modern sawmill does not create value. The value is already inside the log. It arrived with the tree. Everything the mill does from this point forward is an attempt to stop that value from leaking out. Through a wrong cut, a wandering blade, a mislabeled instruction, or a bundle that sits in the wrong corner of a retail yard for 3 weeks. A few millimeters lost on one log means nothing. The same few millimeters, across 1 million logs a year, is a number that changes what a mill is worth. So the honest question is not, how fast can they cut wood? It is this: at every stage between the forest and the framing crew, where does the value go, and what is actually holding it in place? The logs come out of the woods on a forwarder, over mud and rock and shifting slope, then onto a truck, then down forestry roads that were never built for tens of tons in tow. At the mill, something strange happens. The logs are not sent to the saw. They go into water. A mill pond looks like a delay. It is actually the first defense. Wood left in open air keeps losing moisture from the outside in. The surface dries, the core does not, and the log starts checking, splitting along its own grain before a blade ever touches it. The pond holds moisture steady and doubles as a storage yard that can feed the line at any hour. Value is already being protected. Nothing has been cut yet. Then a log comes up the chain, and the decisions begin. A Douglas fir log looks solid from the outside. It is not uniform. Its diameter changes along the stem. It may be oval, slightly curved, wider at one end than the other. That variation is the entire problem. A straight cut through the wrong position turns a valuable board into short stock. A knot near one edge forces a lower grade. The same knot 2 inches over gets trimmed away and costs nothing. Laser heads sweep the surface as the log rolls through the scan zone. Diameter, taper, curvature, surface irregularities. The computer builds a 3D model in seconds. And at that moment, the log stops being a log. It becomes a set of competing futures: 2x4s, 2x6s, long structural boards, short utility pieces, chips, sawdust. Same raw material, completely different returns. The optimizer tests several patterns against each other. One recovers more board feet. Another protects a long, clean section near the outside. A third produces the exact 16-foot stock an order is waiting on. That last input matters as much as the log itself. A mill already sitting on 10,000 board feet of short material gains almost nothing by making more. The selected plan has to fit the log, the expected grade, and the order book at the same time. Then the computer sends an angle to the turner. Hydraulic rollers grip several thousand pounds of wood and rotate it. The center line has to match the digital plan before the primary saw engages. A few degrees off, and the blade enters a knot instead of passing beside it. A shift sideways, and one full-width board becomes 2 narrow pieces worth less than half. That machine is not lining up wood. It is converting a digital decision into a physical position. which is why two Douglas fir logs from the same Oregon truck, same length, same diameter, can receive completely different cuts. The scanner measures what arrived. The order book decides what is needed. The turner connects them. By the time the first tooth reaches bark, the mill has already chosen what the log will become. But that choice is worthless if the instruction loses track of the wood. A modern mill runs two production lines simultaneously. One of them you can see: logs, cants, boards, bundles moving forward on steel. The other one is invisible, and it has to stay ahead. When the scanner finishes a log, the control system opens a record for that specific piece: measured shape, chosen rotation, cut pattern, expected products. That record now has to travel down the line faster than the wood it describes. An encoder counts conveyor shaft rotation to estimate travel. A photoelectric sensor confirms the exact moment a leading edge crosses a fixed point. The PLC uses both to answer one question continuously: where should this piece be right now? Before the log reaches the turner, its rotation command must already be waiting. Before it reaches the saw, blade positions and feed settings must already be loaded. There is no time to calculate at the cutting point. The material may be 4 seconds from one machine to the next. A late instruction slows the line, or stops it, or kicks the piece out. A wrong instruction is worse, because nothing appears to fail. Picture log 41, hanging up for 3 seconds ahead of the turner. Behind it, log 42 keeps closing the gap. An operator clears a loose slab of bark and restarts the belt. The spacing is no longer what the system thinks it is. If the tracking record kept advancing while the wood stood still, the command written for log 41 can now be sitting on log 42. The turner rotates. The saw fires. Every motor performs perfectly. The board is still wrong. That is why position gets verified more than once. Encoders estimate. Sensors confirm. The PLC compares expected sequence against actual sequence. And when the two disagree, the line pauses. A 3-second stop looks like lost production. It is usually cheaper than a fast mistake. The record does not end at the primary saw. Once one log becomes 8 boards, each board picks up its own identity. Cameras read surfaces. Moisture sensors sample. The trimmer receives cut points based on defect location and required length. A grading station routes each piece to the right stack. The wood keeps changing shape. The record keeps going. And this is where it becomes more than logistics. At the green mill, the record describes a wet board straight off the saw, with a predicted grade. At the dry mill, after the kiln, that board is scanned again, and the prediction meets reality. A board expected to grade high reveals a check. Another comes through stable and confirms the original cut was correct. Multiply that by 100,000 comparisons. Now the mill can see which species, which diameters, which cut positions, which kiln schedules produce usable lumber, and which ones quietly generate rework. The conveyor carries material forward. The data carries experience forward. Without it, a mill only knows what it is cutting right now. With it, a mill cuts today's log using what it learned from 100,000 previous ones. Keeping the right command on the right log prevents a disaster. It does not answer the harder question: was that the right command in the first place? The biggest pile is not the best result. 3 different numbers get called efficiency, and they regularly point in different directions. volume recovery asks how much of the log became saleable lumber. It exposes kerf, edging, and trim loss. It says nothing about quality. Grade recovery asks how much of that volume reached the required quality. Value recovery asks the only question that reaches the bank. What is the combined worth of every board, offcut, chip, and byproduct this log produced? Take one log and 3 plans. Plan A yields the most board feet. Many short pieces, several with knots sitting near critical edges. Plan B yields slightly less volume, but protects 2 long clean boards and removes the worst defect with 1 short trim. Plan C yields a mix of 2x4s and 2x6s that matches orders already loaded in the system. A wins on volume, B wins on grade, C wins on order fit. The optimizer has to pick before the saw starts. Defect position drives most of it. A knot near the end comes off with 1 trim. The same knot at midspan forces a shorter board or a lower grade. A check along one edge may let the board be ripped narrower and stay in a product line. A defect running the full width removes it from structural entirely. And then there is the input nobody expects to be technical, inventory. Producing more of a slow-moving size consumes deck space, kiln capacity, and cash. A mill can be holding enormous volume and still be unable to fill the order in front of it. A full warehouse is not a profitable warehouse. Now, the part that gets glossed over in almost every mill tour. You will hear that nothing is wasted. Bark to the biomass boiler, chips to pulp and panel, sawdust to pellets and heat, offcuts recirculated into the line. All of that is true, and all of it is good practice. It is also not the same as protecting value. Turning a clear, straight, high-grade board into chips still destroys value. The chips get used, the board is gone. A closed-loop energy system is a floor under your losses, not a substitute for cutting correctly. And zero residue is not the goal either, because it is not physically available. Every saw consumes kerf. Every edger removes irregular sides. Every trimmer discards damaged length. Some loss is the price of producing straight, standardized, predictable lumber. The goal is controlled loss. Take the bark, not the clear wood under it. Cut around the defect only when what remains is worth more. Shorten a board only when the grade you gain pays for the length you lose. Use the residue well, and don't manufacture residue you didn't need, which means the right answer moves. A dimension that was worth chasing last week may be overstocked today. The log hasn't changed. The correct decision has. That is what a modern optimizer is really doing when it looks like it's just measuring wood. It's weighing geometry against grade, against length, against inventory, against orders, and choosing one pattern out of thousands. On the outfeed, it looks trivially simple. A few straight boards moving forward, chips falling away below. Every one of those boards is a decision that beat 3 other decisions. Software can choose the best pattern. Steel still has to reproduce it. The computer draws a perfect line. The blade works under heat, vibration, changing grain, and a load that shifts every second. Those are not the same conditions. Thin kerf is the obvious win. A narrower blade removes less wood per cut, and across a shift that is real lumber. The advantage exists only while the blade stays straight. Clear wood offers one resistance. Dense late wood, a large knot, or a change in grain direction pushes hard against one side of the blade. If strain is too low, the blade moves. The cut wanders. The board comes out thick at one end and thin at the other, or carries a visible wave across its face. Then the second loss arrives at the planer. To produce a flat board, the planer has to remove material down to the lowest point of that wave, so a thin theoretical kerf, cut with an unstable blade, ends up costing more total wood than a wider blade that ran straight. That is the sentence worth remembering. Thin kerf saves wood only when everything holding the blade is inside spec. Guides control the path right at the cut. Too far from the wood and unsupported blade length increases. Misaligned, and they push the blade off the intended line before it ever meets resistance. Wheels have to track correctly at production speed, and a small alignment error grows as heat builds and the blade stretches. The frame has to resist all of it. A rigid head rig keeps wheels, guides, and blade in the same relationship under load. Flex in the structure changes that relationship mid-cut, which means the geometry you set at zero load is not the geometry doing the cutting. Then power. The motor nameplate is not what reaches the tooth. Only what survives the drivetrain gets there. A loose belt slips exactly when resistance rises. Blade speed drops at the moment more force is needed. The blade heats, and it walks offline. Over-tightening is the opposite failure. Excess tension loads bearings, pulleys, and shafts, and buys an unscheduled shutdown. On some portable wood miser machines, belt tension is verified by applying a specified force, around 14 pounds, and measuring deflection against a figure that varies by model. The exact number is not the lesson. The lesson is that tension is a measurement, not a feel. Feed speed carries the same trap. Too slow, and output falls. Faster than the blade can clear sawdust and hold direction, and cut quality collapses. The fastest setting is frequently not the highest output setting, because 10 seconds gained on one log is worthless against 15 minutes spent changing a damaged blade. This is where people still beat sensors. An operator watches the surface coming off the cut, listens for a change in pitch, checks blade temperature, guide condition, the volume and texture of sawdust leaving the kerf. Sensors can flag vibration or a speed drop. A person confirms the physical cause and knows whether to adjust or stop. The computer knows the planned line. The operator knows whether the machine is still reproducing it. A clean board leaving the saw is proof that 6 things were simultaneously true. The blade held tension, the guides stayed aligned, the belt transferred power, the feed matched the cut, the frame resisted movement, and the wood behaved as scanned. Precision was never one component. It was every component staying inside its range at the same moment. The board survives the saw. It gets planed at thousands of feet per minute, scanned for warp, checked for moisture, stamped, and stacked. The problem still isn't over. Final inspection records the board at one moment in one building. Wood does not agree to stay there. At the mill, cameras catch surface defects. A warp scanner measures bow, crook, cup, and twist, and moisture meters confirm the board is near its target range. A board can pass all 3. That pass does not freeze its shape. Wood exchanges moisture with the air around it until it approaches equilibrium, and it keeps doing that in a warehouse, on a flatbed, in a retail yard, and on an open job site. Direction matters. Wood does not move equally in all directions. Movement across the grain is far greater than movement along it, and the growth ring pattern decides the result. A flat sawn board with one face drying faster than the other will cup. Uneven drying anywhere along the stack produces bow, crook, or twist. So the board leaves Oregon straight, and then the environment starts negotiating. A bundle traveling toward Arizona meets much drier air. One heading to Florida meets humidity and rain. Same board, opposite reactions. Packaging slows this. It cannot stop it. A moisture barrier protects during handling. Steel straps keep the stack compressed. But torn wrap, forklift damage, or rain entering one side creates an uneven condition inside a bundle that looks fine from outside. Ground contact adds a second gradient, bottom layers absorbing while top layers stay dry. Air moves around exposed edges, but not through tight center layers. One bundle can hold 3 different moisture conditions at once, and cutting the straps changes the mechanics again. While banded, boards hold each other in position. Released, internal stress finally has somewhere to go, and a board that was straight inside the pack moves within hours. Then storage. A covered rack on dry blocking protects lumber. An open rack in sun and rain does not. A long board supported at only 2-point sags. A stack on uneven stickers takes a permanent set. By the time a contractor picks up a bowed 2x6, the cause could be any of 6 places, and the blame almost always lands on the mill. Sometimes correctly, sometimes the board left within tolerance and changed in transit. Sometimes the grain was less stable from the start, and a wet corner of a retail yard finished the job. Frequently, more than one of those is true at once. The USDA Forest Products Laboratory in Madison has published decades of guidance on wood and moisture for exactly this reason. The principle is simple. Wood reaches balance with its environment, and that balance shifts whenever temperature and relative humidity shift. The numbers are not universal. Framing lumber, hardwood panel, and engineered beam have different targets. Thickness, kiln schedule, and end use all move the acceptable range, which is why no single moisture percentage explains every bent board on a home center rack. Timing complicates it further. The surface dries before the core. One face takes sun, while the other stays shaded. A board can hold moisture unevenly, while its average reading looks perfectly acceptable. The scanner captures the shape at inspection. It cannot control the weather 1,500 miles away. That does not make inspection theater. It defines what inspection can promise. The mill can reject what is already out of tolerance, dry material toward the required range, and package it to survive handling. The rest belongs to the carrier, the retailer, and the crew. A straight board reaching a customer is the output of accurate sawing, controlled drying, honest grading, protected transport, level storage, and proper acclimation. Miss one, and the value disappears after every machine did its job correctly. Speed films well. A gang saw splitting a cant in one pass. A planer running lumber at 2,400 feet per minute. Those numbers show capacity, and capacity is genuinely impressive. They just don't show the result. A fast line producing the wrong sizes builds inventory instead of revenue. A thin blade that wanders generates rework. A board that passes grading and bends in a warehouse generates a return, which costs freight, handling, replacement stock, and something harder to repurchase, the customer's confidence. So the honest scorecard reads differently. Volume recovery, for how much of each log became saleable lumber. Grade recovery, for how much of it reached the intended quality. Order recovery, for whether the shift actually produced the dimensions customers asked for. Rework rate, for how much conveyor time, labor, and power went into fixing work already done. Downtime minutes, for what blade changes, jams, and calibration stops removed from a line that looked fast all day. Then delivery quality, how many bundles arrived at the required moisture, grade, and shape. A low complaint rate can outperform a small gain in line speed. Residue use belongs on the list too. Bark to the boiler, chips and sawdust to panel, pulp, pellets, and heat. It genuinely raises the value taken from every log. It just has to be read in the right order. Residue recovery counts after. The mill has protected the highest value lumber, never instead of it. And there is one more number, on a completely different clock. Counting seedlings planted describes how much work started. Survival after 1 year, after 5, after 20, describes whether anything was actually established. The U.S. Forest Service keeps those separate for a reason. Young trees face drought, fire, insects, competing vegetation, and browsing. Future supply depends on living stands, not planting totals. Which puts the whole operation in perspective. A scanner decides in seconds. A blade completes a cut in moments. A Douglas fir stand takes decades to become worth scanning. People hold every one of those timescales together. Operators catch the tracking failure. Technicians keep blades, belts, bearings, and guides in spec. Graders judge the borderline pieces. Warehouse crews protect what production already paid for. Foresters check whether the next generation lived. Automation makes the repeatable work fast. People handle the exceptions, and exceptions are where the money is. Look at one finished bundle waiting on a rail car for a construction site somewhere in America. The boards look identical, interchangeable, ordinary. Behind that appearance, a scanner measured an irregular log. An optimizer chose one product mix over 3 others. A PLC kept every command attached to the right piece of wood. A turner held the angle. A blade stayed on line under load. A planer removed only what it had to. A grader routed each board. Packaging held the moisture out. A warehouse kept it supported and flat. No single machine created that bundle's value. Each step stopped part of it from disappearing. That is the difference between cutting wood quickly and running a mill. The fastest machine wins the footage. The controlled result wins the order. If you want more breakdowns of the machines, materials, and decisions behind American manufacturing, subscribe. The next one is already in the cutting plan.